a small number of things. They can read and write to memory, and they can do math with numbers they're holding. Modern processors do other things too, but this is basically it. Now, an executable program, the one generated by the compiler, is just a list of instructions for the processor to follow, written in binary. The instructions are things like read these bytes from memory, do stuff to them, write bytes to memory, jump forward this many lines, jump back this many lines, but only if this flag is set, stuff like that. A program expressed in a list of binary instructions is called machine code, and this is the kind of program that your computer can actually read. But why does a computer processor only read programs that look like this? Why this specifically? Well, in short, here's how a processor works. The processor already contains the circuitry to do all of these instructions, but the correct circuitry only gets connected together when the corresponding instruction gets fed into it. The ones and zeros in the instruction cause certain transistors to open or close, which ends up connecting the correct circuitry together to execute that instruction. If you want to look more into how this works, you might want to check out Crash Course Computer Science, particularly episodes 5 through 8. Episodes 3 and 4 are also helpful if you need a refresher on binary and logic gates. Though you could just watch my video too. And for the record, Crash Course isn't paying me to recommend them, I just really like this series. But in short, just know that executable programs look like this. But when you first learned to program, you didn't need to know anything about these complicated machine code things like memory management, operations on bytes, or conditional jumps. Programming was about variables and if statements and loops and functions. Well, these things are just higher level constructs that make it easier for humans to think about programming. A program expressed in this form is called source code. It's the version of a program that a human understands, and thus the version that most humans actually write code in. The compiler's job is to take this source code that is human readable and turn it into machine code that is computer readable. But how does it do that? How does it turn a string of text into a list of instructions in binary? Let's look at some examples. Here's a pretty simple program. Declare a variable of type integer that we'll call x, then assign it a value of 3. For now, this program only exists as source code. I know it looks like it has some kind of structure, but for the computer, it's just a meaningless sequence of characters. It's just text. And I know this program doesn't really do anything useful, but we're starting simple. Let's pass this source code into the compiler and see what it does. The compiler first divides the text up into individual tokens. It's kind of like the compiler is figuring out what the words are in this program. Then the tokens are organized into a hierarchical structure known as a parse tree, which is like figuring out what the grammar is in this program, the structure. Then the compiler records context about the program, including variable and function names. This is the stuff that a computer needs to keep track of in different parts of the program. In our case, the only context we need is the variable x. Oh, and the main function too, but that's less important for us. The final step is to traverse the tree and figure out some machine code that would effectively do the same thing as this particular source code. I just want to clarify that typically, compilers don't go directly from the parse tree to the machine code. There's usually a few intermediate steps that we're going to skip over. This is what the machine instructions look like in binary. It's a little hard to read and interpret, so let's shorten it by writing it in hexadecimal. Actually, it's still a pain to read. Let's write it out as assembly code, which is a more human-readable version of machine code. That's better. Now, we're going to ignore this stuff here. Just know that it's responsible for starting and ending the main function, which determines where the program starts and ends. This is the instruction that corresponds to the assignment of the variable x. This instruction says to move the number 3 into this memory location. Let's run the program and see what happens. And as we'd expect, the number 3 got put into that memory location. It looks like the compiler decided that this part of memory is where the variable x lives. And that's it. The compiler took our source code, which said to take a variable x and assign it the value of 3, and translated it into machine code, which says to place the value 3 in this part of memory. So our program is kind of boring right now. What happens if we change it? Let's add a line to increment x by 1 after it's been assigned 3. We assign it the value of x's current value plus 1. Now we pass it into the compiler again to generate a new version of our machine code. The compiler finds tokens, parses, contextualizes, and generates. It looks like there's only a single new instruction, to add the value of 1 to this memory location. After all, this is the location that the compiler decided that x lives. Modifying the variable x is equivalent to modifying the value stored in this memory location. Let's run it. The value 3 appears in that memory location designated for the variable x, and then the value becomes 4. Now, so far, we've seen how variable assignments and simple mathematical operations get translated. But it's not so simple for if statements, loops, and functions. There are no machine instructions that are direct equivalents. Instead, we need to emulate their behavior with instructions that do exist. Let's start with an if statement. In an if statement, we only execute the code in this block if this condition is true. If the condition is false, we skip over this code. In assembly, the code inside the block gets translated normally, but before it, we have some instructions for evaluating the condition, and then we have a conditional jump instruction. In this case, to jump past the block we want to skip, but only if we're supposed to skip it. The processor knows whether or not we're supposed to take this jump based on the result of the previous instruction. That instruction temporarily set some flags in the processor so we could remember the result by the time we got to this conditional jump to skip over this block. If we're not supposed to skip it, then the processor ignores the jump and continues normally, conveniently executing the code inside the block. Notice that these machine instructions are effectively doing the same thing as our if statement? Let's see how jumps can emulate other source code behavior. There's the if-else statement. Only execute this block if the condition is true. Otherwise, execute this block. In assembly, we have the code in the first block and the code in the second block. Before the first block, we have a comparison and conditional jump, like what we had earlier. In between the blocks, we have a regular non-conditional jump instruction. This is so that execution skips the second block if it just finished the first one, which is kind of how the if-else statement works if you think about it. Then there's the while loop. Only execute this block if this condition is true, and keep executing it over and over again until it's not true anymore. In assembly, we have the block's code, the instructions to evaluate the condition, and the jumps emulating the loop. Functions are a little more complicated. Basically, functions encapsulate a code block so that it can be used in multiple parts of a program. Most programmers out there should know that they also isolate context and they can do recursion and stuff. This is what its equivalent assembly code looks like. Let's run it to see what it does. Hitting the function call, we save all context into memory, allocate new space on top of it, execute the function code, which may involve calling more functions, and pop back down once it's done. This makes it possible for functions to call other functions or even themselves. You just push more memory and pop back down when you're done. So that's how compilers work. They take your source code and make machine code. But there's one problem. If you compile your program on one computer and then copy it over to another computer and try to run it, it might not work. If the new computer has a different operating system or has a different processor model, it probably uses different machine instructions. So, if you want your program to be able to run on this new computer, you better be able to compile to that computer's machine code. And if your program's users might run your software on different platforms, unless you're distributing the source, you're gonna need to keep a copy of an executable for every platform you want to run on. Every single one. Some languages like Java sneak around this issue. Instead of machine code, Java gets compiled to an intermediate representation known as bytecode, and then the bytecode can get sent to other computers, where it gets converted to that specific computer's machine code when the program is run via an interpreter. It's a bit of a compromise. You get better portability, though it's less efficient. But regardless, the language you write your code in is compatible with a wide variety of processors and operating systems. Can you imagine what it was like back in the day when computer programming meant putting assembly or even machine code onto punch cards? Not only would you need to figure out the correct holes to punch for each instruction, you wouldn't even be able to use your program on a different computer model because the other model expected you to punch different holes. Things are a little nicer these days. You just write a program, compile it, and test it with inputs and outputs. If only it were that simple. All thanks to the people who wrote the special program, the compiler. But remember that the compiler is a program itself. If people use compilers to develop programs, how was the compiler developed? Well, it was probably written and compiled in another language, or even the same language, compiling a compiler with a previous version of itself. If we follow this chain backwards, at some point, we reach the origins of development tools, programs written directly in machine code that help you write other programs, literally automating part of the process of creating automation. The history of computer languages is pretty complex. No wonder it took decades to get where we are now. Remember that the next time you're writing code. We have all these beautiful things like syntax highlighting, static analysis, object-oriented programming, functional programming, libraries, linkers, build tools, and debuggers. But it's still amazing that we can just tell our computers to follow our exact instructions at the push of a button. No, wait. There we go. The push of a button. Programming isn't so hard.